Right. Here's a differential equation. This time, I don't have derivative with respect to x, so this is what we call the Dirichlet boundary condition. It's not Neumann boundary condition. And the initial condition looks kind of weird, but later on you'll see that this actually makes the question very easy. And let me tell you why it is so. All right, solution. First, what's the method of separation of variables? You assume that the solution looks like a function of x times function of t. That's what the method of separation of variables means. You're separating x and t. And then you are looking for the solution of the first two, which will give you the general solution by adding all these types of solutions. Okay. All right, let's plug them in. If you plug this to the first one, you get x of x, t prime of t equal to 0.3 x of x, t of t. Well, this time it's differentiated twice in x, so that's x double prime of x. If you plug this into the second one, it's x of 0, t of t, because you're plugging in 0 into x. T is just t. And this one says it's x of 5 and t of t, and that has to equal to 0. And a little note here, if I have t of t equal to 0, that would make this original thing just equal to 0 for any x and t, and that's called a trivial solution. We don't want that. Therefore, you want to just take the case when x of 0 and x of 5 is equal to 0. That would be the only way you can have a non-trivial solution from this method. Okay? So that's something that we immediately get from the boundary conditions. Now what about this one? This one you divide it by 0.3 x times t, xx times t of t. You always divide by the k times x times t both sides. And that's what makes the separation of variables work. Dividing these two, xx cancels and you get t prime t over 0.3 t of t. Whereas on this side, t and t cancel, 0.3, 0.3 cancels, and you get x double prime t over x of t, no, x of x. And because one side it says it's a function of t, on the other side it says a function of x, this side says whatever that function is, it has nothing to do with x, right? This side says whatever this function is, it has nothing to do with t. And what's a function that has nothing to do with t or x? That's a constant function, right? So we know that it's a constant. Usually people use lambda for that constant. And for some reason, instead of calling it lambda, we're going to call it negative lambda. Why? We do that because if we take this equation and rewrite it, we get a familiar equation, x double prime equals to lambda x, which gives you negative lambda x, which gives you x double prime plus lambda x is equal to 0. All right? With the boundary condition that at the endpoints it should be 0. Now, what kind of function has 0 at the endpoints? Sine or cosine? Sine. So this says, oh, we're looking for the sine functions that are 0 and 5 at the endpoint. So the functions that satisfy such a thing is like sine of n pi over L. L is 5 for our case because of that. So these are the functions which are 0 at 0 and also at 5. If you plug in 5, you get sine of n pi. We know that sine of n pi is 0, right? So those are what we call non-trivial solutions or the eigenfunctions. And if you plug this back in here and get the lambda value, you'll see that lambda must be n squared pi squared over 25 with n being 1 to 3 and so on and so on. Okay? So those are the solutions. Now let's also solve t prime over t equals 0.3 equals to negative lambda. Now I can multiply the 0.3 on this side. And here's another way to solve this equation. Just integrate both sides by t. Now what's the integral of a function's f prime over f? What's the integral of that? It's the ln of the denominator, okay? Negative 0.3 lambda. And therefore, if you solve for t by exponentiating, you get t equal to e to the negative 0.3 lambda. But lambda is that thing, so it's n squared. Oh, sorry. If I integrate this side, I should have a t there, right? I forgot that t. So that's the function t. And because our original solution looked like x of x times t of t, multiplying these two, I get what u of xt is. U of xt is product of sine n pi over 5x times e to the negative 0.3 n squared pi squared over 25t. And then we take the linear combination of those functions to generate the general solution for this. So what do? We take Cn, some general coefficient, and sum it over n from 1 through infinity. Okay, so that's going to be the general solution that satisfies the first two. And now all you have to do is to make this initial condition work. Okay. How do you make it work? Well, just write it down. What is ux of 0 for this? What's ux of 0? You're plugging a 0 into what? T. So e to the 0th power. What's e to the 0th power? 1. So you have sigma n from 1 through infinity, Cn, sine of n pi over 5 x. On the other hand, this should equal to, it has to match with our initial condition, right? Which is sine of pi over 5 x plus 5 times sine of 3 pi over 5. Now, because the left side looks like something times sine, it suggests that you should take the Fourier series of the right side so that it looks like this, right? Well, if you look at this, it's already in the form of sine, right? So you can say that this is a Fourier series already. What's a Fourier series again? You're trying to represent the function as sum of sines and cosines, right? It's already in the form of sum of sines and cosines. It's already a Fourier series. Now, the left side requires Fourier sine series, and look, it's already Fourier sine series. Right? So that means we can just compare both sides to figure out what Cn's are. Okay? All right. So let's see what this really means. This summation means C1 sine of what? 1 pi over 5x, right? Plus C2 sine of 2 pi over 5x plus C3 of sine of 3 pi over 5x plus C4 of, I don't know, so and so, okay? Now, comparing this left side to the right side, your conclusion is that C1 is? C1 is? Okay, maybe the easier one is this. What's C3?
5.
5. This
C1
number.
is 1.
Yeah, C3 is 5, and once you figure that out, you can see that C1 must be 1. Because this and this, for these two to be equal, C1 must be 1, right? Now what about C2? C4? C5? Everything else will be 0, just this one, okay? Therefore, if you plug in C1 equal to 1, C2 equal to 0, C3 equal to 5, and C4 equal to 0, and on to the original solution. This was the general solution, remember? If I plug those back in here, we get the following answer. Let's write down the answer. The answer is that what was represented as an infinite series is actually just two terms. One is when C1, when you have n equals to 1, C1, and C1 is 1, so it's 1 times sine of pi over 5x times e to the negative 0.3 times 1 squared is 1, so it's pi squared over 25t, plus C2 is 0, so I don't write that. C3 is 5 sine of what? 3 pi over 5 x e to the negative 0.3, and then 3 squared is 9 pi squared over 25 t. And then what do you have? Nothing. It's 0 afterwards. So if you expand this with these values, C5 is 0 and 0 afterwards, then everything is 0, so you only get 2 terms. Okay. So that turns out to be actually a simpler problem than the previous ones because your solution, your initial condition is already in the form of a Fourier series.